Okay, so this is 14.2. In this section, we're going to be finding volumes underneath surfaces. So in the picture I've drawn here, I have a surface up here. And on the bottom, we have a rectangular region down here. So my rectangular region is from A to B on the X. This is the X-axis here. From C to D on the Y. This is my Y here. That's my Z up that way. Okay, so I've divided the rectangle into smaller little rectangles, as you can see in here. I want the spacing between all the rectangles to be the same sizes, and let's say they're delta x this way, so from here to here, and along this way I want them all to be delta y. So to get that, then delta x would be b minus a over n, say you have n of them this way, and delta y would be c minus d over m. So say you have m of them this way. Okay, so I'm looking at a typical little guy here, and looking, so that's this guy here. I'm looking at the volume above that. I'm calling that Vij. So I could find the little volumes for each of these little rectangles in there and add them all up, and that would give me the volume of the whole region. So in particular, I would have this equation here. Would have that if you add up all the Vij's, it would be a double sum, because you got this way and that way. That will give us our V. Okay, so I've included a picture of this in the online material, so you can look at it some more, because I'm going to erase it now. So, okay, let's keep going. Okay, so I'm going to erase this picture, and I'm going to draw an exploded view of the Vij guy. So let's do that. Okay, so here is an exploded view of Vij. So the left end point is xi, yj, and this is the x-axis going this way and y-axis going this way. So as we mentioned in the other picture, if you go back and look at it, the thickness here was delta x for each of the rectangles, and this way is delta y. And the height at this point, or the z value, if this is xi yj, the height would be f of xi yj, the height here. So we can say, note that Vij be approximately equal to, so pretty much if you choose delta x and delta y small enough, this is almost flat up here. If it's a continuous function, we're assuming it's continuous. This is almost flat up here, so you could say it is roughly equal to f xi yj times the area of the base. So that's the height times the area of the base. The base would be delta x times delta y. Okay. So as we mentioned, the picture of V is then the double sum of the Vij's. First one I going from 1 to n. Second one j going from 1 to m. And this is true for any m and n. So in particular, you could let them go to infinity. So you could say then this will equal then limit m goes to infinity times summation j going from 1 to m, and limit actually, let me rewrite this. So it'll equal then here, let's put both limits on the outside. So limit m goes to infinity, parenthesis, limit n goes to infinity, summation j equals 1 to m, I equals 1 to n, Vij. Now in the limit, the Vij and this will start to equal, because as we said, when delta x and delta y get smaller and smaller, this approximation will be better and better. So we can say this will equal then limit m goes to infinity, limit n goes to infinity, j goes from 1 to m, I goes from 1 to n. Now in place of Vij you can write f xi yj delta x delta y. I can then bring this limit with the n over here, so I'll write like this then. We actually write it over here. Equals then limit m goes to infinity. So it will be summation j equal 1 to m. Then it will be limit, bringing the limit n inside, n goes to infinity of summation I equal 1 to n. So it'll be f I yj delta x, and let's go like this, put the delta y here. Okay, but now this is right here, this part here is a Riemann sum of definition of integral, so we can then write this as limit m goes to infinity summation j equal 1 to m. Then here it's going to be integral, so it's on the x, and if you go back to the first picture, the x went from a to b, so it's going to be from a to b f of x y j dx, and then dy on the outside here, or delta y, sorry. Okay, let's keep going. That's a comma there. So then this is also Riemann sum here. So our final answer then will be here, integral. So this is on the y, and the y went from c to d. If you go back and look at the picture at the beginning, then integral a to b f xy dx dy. So showing then the volume can be represented as a double integral over the surface. In a similar way, we could switch around these two limits here and these two sums. If you did all that stuff, you could then show that pretty much I could switch around the integrals then to be a to b, c to d, fxy dy dx. Okay, so I can switch the order of integration around. This is just when you have a rectangular region. We're going to show it's not always that easy to switch the order of integration around. So I switch the order here and I switch the dx to dy. That's true for the rectangular region. Okay, so that's the formula for the volume now. So let's look at an example next. Okay, so here's an example. So we've let R be the region, rectangular region. X goes from 1 to 2, y 0 to 3. So we define this double integral over our fxy. This is our fxy here. Okay, so this will equal then integral. So we're doing x first, so it'll be 0 to 2. Then we're doing y second, so it'll be 0. Sorry, this is 1 to 2. And y is 0 to 3. It'll be our 2xy plus 3x plus y plus 7 dx dy. Okay, so dx means integrate with respect to x. We're going to treat the y as a constant. So let's do that first. This will equal then 0 to 3. So integrating 2x is going to be x squared. Y integrating 3x be 3x squared over 2. Integrating y, it would just be yx, treating y like a constant. So it'd be yx. And integrating 7, so it'd be 7x. And we're going to evaluate this at our 1 and 2. Then we're going to do dy after that. Okay. So we're going to put 2 in place of x everywhere, and then subtract, put 1 in place of x everywhere. So we then integral 0 to 3. So putting 2 in place of x, it will be 2 squared y plus 3 2 squared over 2 plus 2 in place of x will be 2y, and 2 in place of x here plus 14. And from that, we're going to subtract then. So putting 1 in place of x, so it'd be 1y 3 halves. So 1 in place of x plus y plus 7. This will be all times my dy still. Okay. Okay, let's bring it down here. So it'll be 0 to 3. So you got a 4y there, and the 2y's will be 6y, then minus 2, so it'll be 4y. And then this 2 will cross off with the 2 up there. So it'll be a 6 left, and that's still plus 14. So plus 14, and then minus 8. So it'll be 4. Sorry, it'll be 6. It'll be 20 minus 7, so it'll be 13. And then you'll still have this minus 3 halves here. Okay, and now we'll be integrating this with respect to y. So integrating this now, it'll be 4y squared over 2 plus 13y minus 3 halves y, and then evaluate it at 0 and 3. Okay, so let's keep going here. So putting 3 in and putting 0 in. You put 0 in, it's gone, so it's just going to be putting 3 in here. And that's going to be a 2 there, so it'll be 2 times 3 squared plus 13 times 3 minus 3 halves times 3. It's going to be 9, so it'll be 9, so it'll be 18 here, plus 39, so it'll be 18 plus 39 minus 9 over 2. So it'll be then 57 minus 9 halves. Then changing everything to halves, so it'll be 57 times 2 minus 9 over 2. And let you check, that becomes 105 over 2. Okay, so that's our answer. Now let's do part B. So part B is the same fx y function, same region, except now I'm switching around y and x. So this will be then, this should give us the same answer. So it'll be double integral 2x y plus 3x plus y plus 7 dy dx. Now the dy is first, therefore we're going to go from 0 to 3. And then the x is second, so it'll be 1 to 2. Okay, so I'm going to integrate with respect to y first, since I have to dy first. So I'm treating x like a constant. So it'll be then double integral 1 to 2. So integrating with respect to y now, so it's going to be x y squared for this guy. 3x is a constant, so when you integrate it'd be 3xy. Integrating y with respect to y will be y squared over 2. And integrating 7 with respect to x will be 7y. And we're evaluating this at 0 and 3. So now the 3 is going to go in place of the y everywhere, and then minus the 0 in place of y. So this is then to be, oh, I forgot my dx here. Dx. So this will be then integral 1 to 2. So putting 3 in place of y everywhere, it will be x times 3 squared plus 3x times 3 plus 3 squared over 2 plus 7 times 3. Then when you put 0 in place of y, it'll make everything 0, so it'll be just minus 0 then. That will be dx after that. Okay, so let's keep going. Okay, so keep going here. Should be integral 1 to 2. So we have a 9x here, another 9x, so it'll be 18x. And we have a 21 here. And this will be 9 halves here. Now I'll be integrating with respect to x. Okay, so let's keep going. So integrating with respect to x now, this will be 18x squared over 2. This will be 21x. This will be 9 halves x. Then evaluate it at 1 and 2. Okay, so I'm going to put 2 in place of x and put 1 in place of x. So putting 2 in place of x, that's a 9, so it'll be 9. Putting 2 here, it'll be 2 squared plus 21 times 2 plus 9 over 2 times 2. Then minus, put 1 in place of x everywhere, so it'll be 9 from this one, plus, put 1 here, 21, put 1 here, plus 9 halves. Okay, let's keep going. So this should end up being the same answer. So our first answer was 105 over 2. So let's hope we get 105 over 2. Let's keep going. Okay, so this guy will be then 36. This will be 42. 2's will cancel, it'll be 9. And minus 9. Minus 30. Just combine those. And then minus 9 halves. Okay, so adding this will be 78 plus 9, so it'll be 87 minus 30, so 57 minus 9 halves. Then changes to halves, so it'll be 57 times 2 minus 9 over 2. And you can check that's 105 over 2 also. So same answer as it should be. Okay,